In this video, we're going to take a look at the characteristics that define an ideal op-amp. So the ideal op-amp is a very useful design tool, but we must be mindful of the assumptions made when we are talking about ideal in this sense. So we'll discuss some of those assumptions here. So what do we mean by an ideal op-amp? Well, firstly, an ideal op-amp needs to have infinite input impedance. This means that no current is going to be drawn into the inputs. So it doesn't matter what your input circuitry has, there'll be no current drawn into the op-amp because it has this very high, in this case infinite, input impedance. So there'll be no current lost across it. Of course, in reality, there will be some small current drawn into the op-amp, but generally, when designing op-amps, you want to get them to be as ideal as possible, so that would be minimized. And that's true of both of our inputs. Input 1, the inverting input, and input 2, the non-inverting input. Our second criteria is to have zero output impedance. So the opposite requirement to the input here, we want our output to have zero impedance. This means that if you connected a load resistor at the output of your op-amp, then that's the only resistance you see. There wouldn't be a series resistance combined with that, and your op-amp can theoretically provide as much current as needed to that output circuitry. So whatever load is put there at the output, it won't change the output characteristic of the op-amp. Of course, in reality, we won't be able to get zero output impedance for any circuitry, but we'd design it to be as low as possible. The third criteria is for infinite open loop gain. So open loop gain here, denoted by A, this is the amplification that our op-amp is going to provide. So op-amps work as a differential amplifier. They amplify the difference between the two input voltages. So you can see in the middle here, our output is V2 minus V1 times A. So what we're saying here is for an ideal op-amp, this A should be infinite. Of course, that's not very useful in a practical circuit. Any difference in input will of course be boosted up to infinity, but when we combine that with feedback, you'll see that that becomes very useful for the mathematics, and you can design your op-amp to have a controlled gain, which we'll go over in some of the subsequent videos. Next criteria is for zero common mode gain. So the common mode gain is the unique case when V2 and V1 are equal. So if V2 equals V1, then there is of course no difference here. This part of the op-amp output equation should be 0, and there should be no gain at that point. So of course in reality there may be some base level gain here, and that would effectively be noise at your output that you wouldn't want. So in your ideal op-amp, we really want zero common mode gain. So a V out of 0 if our two inputs are identical. There is one further characteristic for an ideal op-amp, and that is infinite bandwidth. So that is to say that the operation of the op-amp won't be affected by the frequency of the input signal. So you wouldn't have to worry about very high frequency, very low frequency signals. But again, in reality, that will not be the case, and op-amps do have frequency dependent characteristics, which again we'll look at in more detail in the lectures. So that concludes our overview of the ideal op-amp.